Up on the chalkboard I have several elements from the periodic table, and they're on circles of different size and color. The sizes are meant to represent the atomic weights or atomic masses of the elements, and the colors are meant to represent their chemical properties, how they react or don't react with different materials. And what I want to do is a little demonstration of how the periodic table was invented by the Russian chemist Dmitry Mendeleev. So what I'm going to do is I'm going to go over and I'm going to begin putting those elements in order from the smallest to the largest. This will take just a second here. We'll zoom back out. Okay, here I go. Okay. So, a similar activity was pursued by Mendeleev one night in his little shack on the Black Sea in Russia. What he was doing was he was trying to organize what was understood about the elements at the time. On little cards he wrote the names of the elements, their atomic masses, and the chemical properties of the elements. And when he arranged them according to size, he noticed that there was another pattern. Now you might be able to see this pattern. I'll zoom in a little bit closer. It has to do with the colors. The colors here represent the chemical properties of the elements. Elements that have get that focused. Elements that have the same color have similar chemical properties. He saw that the properties repeated themselves. You can see that the order goes green, yellow, orange, red, pink, pinker, and then blue. And then it repeats itself again. Green, yellow, orange, red, pink, pinker, and blue. And so when it repeats itself like that, we say something that happens over and over again happens periodically. That's where the periodic table got its name. So what he did then was he took those elements and rearranged them. He took all the elements and put them out again according to increasing size. But then when the pattern of properties repeated itself, he started a new row. So that elements that had the same chemical properties ended up in columns. Now there's a blank space right here where there's no element. And the reason is because at the time that Mendeleev did his work, some elements hadn't been discovered yet. And he left open those spaces on his periodic table and predicted that one day an element would be found that had the same chemical properties as these, and that had a mass that was somewhere in between these. So the periodic table was invented as a way of trying to make sense of all what was understood about the elements, about their masses, and if they're in any way related to their chemical properties. And in organizing them this way into groups that have similar chemical properties, Dmitry Mendeleev invented the periodic table. In our experiment, we worked with some of these elements, and we're trying to find out why they're arranged the way they are in the periodic table, what it has to do with their electron configurations as well. So let's take a look at the results from our experiment. Let's look at the results of our experiment, chemical properties of elements. What we'll do is look at our data and observations and discuss things to think about when answering the questions. At the end, we'll make a prediction about the reactivity of an element that we didn't test, and we'll try testing our prediction to see if it turns out the way that we think it should. So let's start by looking at our data and observations on the back of the first page. So what we were doing was we were taking 6 different compounds that contain metal and a nitrate, the metals, lithium, sodium, potassium, magnesium, calcium, and strontium, and combining them with these 3 compounds that contain ammonium and a negatively charged ion, chloride, carbonate, and phosphate. In these metal nitrates, the metals react by losing electrons to become positively charged ions, joined to the negatively charged nitrate. These compounds may or may not react with these 3 compounds, and we're trying to find out which ones do or don't react. And so what we observed was that the ammonium chloride compound did not have any reaction with any of the 6 metal nitrates that we tested. In fact, these first 3 metal nitrates didn't have any reactions with anything that we tested, with ammonium carbonate or with ammonium phosphate. The magnesium, calcium, and strontium nitrates, though, did react with the ammonium carbonate and the ammonium phosphate, and we saw a cloudy mixture. Looks like this. This was the one from trial number 10 with magnesium nitrate and ammonium carbonate. Let's look a little bit closer at what's going on in that reaction and just refresh our memory on what is a double replacement reaction. So just focusing on this trial here in cup number 10, where the magnesium nitrate and the ammonium carbonate were combined and a reaction was observed. What's really going on in there? So the magnesium nitrate and ammonium carbonate are both soluble ionic compounds. That means that when they were put into the water, these two parts, the positively charged part and the negatively charged part, separated from each other. And that allows them to rearrange and recombine to form new substances. So for example, the magnesium positive charge and this carbonate negative charge from the two different compounds can join together to form a new combination, and that would be magnesium carbonate. Likewise, the ammonium positive charge and nitrate negative charge of the two compounds can rearrange to form a new compound, and that would be ammonium nitrate. Now the real question is, when these materials were recombining and we saw a chemical reaction occur, which part of the compounds was it that was reacting? Was it the magnesium part, the nitrate part, the ammonium part, or the carbonate part? When you see this white cloudy stuff in there, what is it really, and how can you tell? Well, let's take a look at all the different combinations that you can make when you join together these compounds. Whoops. One thing that all 6 of these compounds have in common is they contain the negatively charged nitrate ion. And one thing that all these compounds have in common is they contain the positively charged ammonium ion. That means that when these 6 compounds and these 3 compounds join together, all 18 combinations have in common one compound that they can make. They can all make ammonium nitrate, because ammonium is in all 6 of these, all 6 of these, all 6 of these, and because nitrate is in all of these and all of these and so on, every single one of these 18 cups could have made ammonium nitrate. And so then when you see that there's a reaction, when we see these 6 cups show a reaction, where the magnesium, calcium, and strontium compounds were reacting with the ammonium carbonate and the ammonium phosphate, well, in those reactions, you can tell that what wasn't happening was that ammonium and nitrate were joining together to form the new combination. You can tell that because if they were, you would have seen cloudy reactions in all 18 cups. So for just looking at this one cup, cup number 10, where there's the cloudy material, we can tell that the cloudy material in there is not the ammonium nitrate. We can tell that, one, because if it were ammonium nitrate, then all 18 of the cups would have shown a reaction. Another way that we can tell is by looking at the solubility data that we discussed with the demonstration at the beginning of the experiment. The 3 compounds that you were using that contain ammonium are all water soluble, and then there was one that you didn't have at your bench that I demonstrated is soluble, ammonium nitrate. And if you put a little bit of that into water and mix it around, the water stays clear and colorless. So ammonium nitrate, the one combination that all 18 cups could have made, is a water-soluble substance. So when you see something that's cloudy like that, you know for sure that it wasn't the ammonium and it wasn't the nitrate that reacted. It was the other things. It was the magnesium and the carbonate, or the calcium and the phosphate, or the strontium and the carbonate. It was not the ammonium and the nitrate. So we know for sure that when we were looking at these results, that it was about the metal parts of the compounds that made the reactions react or not. So if that's the case, let me keep this down here. If that's the case, then we can divide up our compounds into 2 different groups. We can divide those into these 3 here that react, that don't react, and the other 3 that do react. So lithium, sodium, and potassium all can belong to one group of elements that were tested that don't react with any of the substances that we used. And the other three, magnesium, calcium, and strontium, they can be grouped into the elements that did react. Now let's look at where those are on the periodic table. So those elements are over on this side of the periodic table: lithium, sodium, potassium, magnesium, calcium, and strontium. Just looking a little bit closer at them. So the ones that we saw that were able to react, they all belong to the same group on the periodic table. They're all in group 2. And the ones that didn't react, they're all in the same group on the periodic table, group 1. Elements are grouped on the periodic table according to their shared chemical properties. Elements that were placed in the same group by Dmitri Mendeleev when he invented the periodic table, they were placed in the same columns because they had similar chemical properties. And that's what we observed in our experiment. He may have used results like these in the making of his periodic table. Now, why do they have these properties? At the time that Mendeleev was inventing his periodic table, he didn't have any idea about the structure of atoms because that hadn't been discovered yet. He didn't know about electrons and protons and neutrons and things of that nature. But now that we do have a picture of what's going on with the electrons inside of atoms, we can come to a deeper understanding of why we see these patterns in our reactivities. So what I'd like you to do is to try first writing out the electron configurations of the elements that we were testing: lithium, sodium, potassium, magnesium, calcium, and strontium. Write those out yourself first, and then we'll check our answers together. Okay, now you've had a chance to write out those electron configurations. Let's take a look and see how you did. So I wrote out the 3 electrons for lithium, the 11 electrons for sodium, and the 19 electrons for potassium, 12 for magnesium, 20 for calcium, 38 for strontium. And what we're going to look for in their electron configurations is which are the outermost electron orbitals, the ones that are in the biggest energy level number orbitals, the ones that we call the valence electrons. And you tell that by looking at the energy level number. So for example, in lithium, these are the electrons that are in the outermost or valence electron orbital. And for sodium, in the 3rd energy level, that's the biggest energy level. And in potassium, the 4th energy level. Those are the biggest, that's the biggest electron orbital in that element. For magnesium, it's the 3rd. And for calcium, it's the 4th, and for strontium, it's the 5th. Now, looking at those outer electrons, look at how many valence electrons there are in these elements. Lithium, sodium, and potassium all have in common that they end with an s orbital with 1 valence electron. Magnesium, calcium, and strontium all have in common that they end with an s orbital with 2 valence electrons. The elements that are arranged on the periodic table by their shared chemical properties also share something about their electron configurations. Elements that are in group 1 all have 1 outer electron in an s orbital. Elements that are in group 2 all have 2 outer electrons that are in an s orbital. So the ones that had no reactions all had this outer electron configuration. The ones that had reactions all have this outer electron configuration. When elements have the same outer electron configuration, that confers on them similarities in their chemical properties. That's why when Mendeleev made his periodic table, the elements lined up this way with shared properties, because they also had shared electron configurations, shared valence electron orbital configurations. Now, with this in mind, suppose we were to do an experiment to test an element that we didn't try. Let's say that we had a sample of barium nitrate, and we wanted to combine that with the carbonate and the phosphate and the chloride that we did in the original experiment. What do you predict would happen? So what I'm saying is, if we had another trial, and in that trial we had barium, and we combined it with ammonium chloride, ammonium carbonate, and ammonium phosphate, what would you predict would happen and why? Well, if you look at where barium is on the periodic table, it's in the same group, the same second column as magnesium, calcium, and strontium. And since these three all had a similar chemical property, that they reacted with carbonate and phosphate and not with chloride, and because they also have in common that they have two outer s electrons in their valence electron orbital, barium, you would predict, would have similar chemical properties, that it would do the same thing. We can test that prediction using the same procedures that we did with the first part of the experiment. Okay, we'll test our hypothesis by using the same steps that we used in the first part of the experiment. Here I have a solution of barium nitrate and water, and you can see that it's clear and colorless, just like the other metal nitrates that we used. And I have the original solutions of ammonium chloride, ammonium carbonate, and ammonium phosphate. So when I put this barium solution into each of these beakers, and then I test it with the chloride, carbonate, and phosphate solutions, we're predicting that we'll see the same results that we saw for magnesium, calcium, and strontium, since barium is also in that group. So let's check chloride. Okay, I don't see any cloudy reaction. We'll check carbonate. Okay, looks like something's going on there. And we'll check phosphate. All right, another cloudiness. So the chloride didn't react. It didn't react with any of the substances that we tested, group 1 or group 2. But the carbonate reacted with the barium, just like it did with the other group 2 elements. And the phosphate reacted with the barium, just like it did with the other group 2 elements. Elements are placed in the same groups on the periodic tables because they have similar chemical properties. And the reason for those similar chemical properties is the underlying arrangement of electrons, particularly the valence electrons in the outermost electron orbitals that are involved in making chemical bonds between atoms to form compounds by either gaining or losing electrons.